Today, edge devices have different computational capabilities and we're required to train speech recognition models of different sizes to be deployed on them. Our work proposes a technique to jointly train speech recognition models for different computational capabilities along with improving their performance. We use knowledge sharing to achieve an improvement in the performance of models of different sizes. Knowledge can be shared between models in two ways. One of them is to share the modules themselves, and the other is to align the output distribution of different models through knowledge distillation. Co-distillation is a technique where models are jointly trained from scratch while simultaneously sharing the knowledge from a teacher to a student model. Co-distillation has been previously used in image classification related tasks like in this NeurIPS 2018 work. This method uses shared low-level layers which then separate into multiple branches. The entire model is trained end-to-end to optimize for the ground truth as well as perform knowledge distillation. One of the popular on-device ASR architectures is the RNN-T model that contains an acoustic encoder, a label predictor, and a joiner. Our proposed collaborative training architecture combines shared modules and co-distillation in an RNN-T model. In the example shown here, the encoder consists of three branches that share a few layers in the beginning. The branches contain different number of layers and hence leads to different number of parameters in each of the branches. We use an auxiliary task of frame-level chenone prediction, and this is where we apply the co-distillation laws using the chenone output probabilities. During training, the branches are trained jointly, and during deployment, we keep only one of the branches along with the low-level layers depending on the required model size. The first component of the overall training objective is the RNN-T loss that is summed over all the branches. The second and third components are the frame-level cross-entropy loss and the KL divergence loss between the outputs of the encoder branches. The Genome targets for training are obtained from a hybrid ASR model that was bootstrapped using the Caldi LibriSpeech recipe. We identify the largest branch as the teacher model and form pairs with the remaining branches as the students. This table shows results for a model trained with 4 branches where the number of layers ranges from 20 to 10. The baseline models are trained individually without any shared modules or code distillation. We also show results for an individually trained model with the frame level auxiliary task. Compared to these baselines, our proposed model with shared modules and code distillation can provide around 3 to 11% improvement over the baselines. In this table, we show results for a collaboratively trained model with 3 branches. It contains an interesting result where we found that the version which doesn't use shared low-level encoder layers provided the best performance among all the settings. Overall, the results indicate that collaborative training is beneficial when training multiple models. However, it also requires some amount of hyperparameter tuning for the desired case. To recap, we have proposed a collaborative training architecture that combines shared modules and code distillation in an RNN-T model. We showed that this architecture is beneficial when training models of different sizes on the LibriSpeech dataset.